Okay, we have finished chapter 18 where we talked about electrical forces, capacitors, insulators, and the important law which was Coulomb's law. And we defined the Coulomb's law, as you know, is a force which is k times two charges. Both are absolute value, no negative, no positive. So we define F equals k times Q1, Q2 over R square. R is the distance between two charges. Now we'll be talking about, we'll talk now on chapter 19, which starts from page 514, about electric potential energy. As all of you know, you have already studied the potential energy and kinetic energy. Potential energy is defined to be the object at a distance or object placed at a distance, then travels, let's say, to the ground. So the height, which is from where it was, and the height it falls to the ground, let's say it was 10 meters. So we multiply force times 10 meter. Force here is the weight, which is mass times acceleration due to gravity. The same principle is applied for electric forces and electric potential energy. Look at the diagram you have, rather the figure you have, 9.1 on page 514. The object is placed at an height A, where let's say the value of HA could be 10 meters, 15 meters, any number. It dropped to a height which is B, and let that height be HB. So difference between these 2 points A and B is the distance traveled, and force here is mass times acceleration due to gravity. Force here also is mass times acceleration due to gravity. It is not changing, the force remains the same, only distance changes. So the gravitational force as defined is mass times acceleration due to gravity. So we can calculate the force from force, the work done, which is gravitational force between the two balls which fall from a height A to B. Height wise it is HA to HB. Okay, as all of you know, work done is force times distance. Here the force is mass times acceleration due to gravity, and distance here is at a point A it is HA, at a point B is HB. So work done will be difference between these two factors, which is defined to be m times g times HA minus m times g times HB. The first one, as you see in this box, we have initial gravitational potential energy, which we can write down in a short form GPEA, and this the final potential energy, which is again gravitational potential energy at B, which is GPEB. So difference of these two will give you the work done. And again I wrote down here force is mass times acceleration due to gravity, which is Newton's law. Work done is the difference between these two potential energy, which are gravitational potential energy. Then we now go to define the electrical potential energy, the next topic. Okay, you can refer to figure 2, page 515. There are two plates, as you see. One is positively charged, other is negatively charged, and we have a test charge which is being pulled out of the positive place you have here, and the charge slowly comes down and hits the negative charge. as you see here, the positive and positive, they will repel each other because the charge positive here for the plate and the test charge here is also positive, so they will repel each other, and slowly the charge is coming down and down, and the negatively charged plate, the charge will hit, which is a positive charge, and there will be charge of attraction. Here the force is Q0 times E, which is electric field. We already defined electric field in chapter 18, where the electric field is total force divided by the total charge. Here we have just rewritten the same equation, only we are interested in force, so we'll write down force equals Q0 times E. Excuse me. Q0 is the test charge, which is positive charge, and the distance is traveled from A to B. Okay. So now we have, I rewrote again here, the positive test charge is Q0. It moves from a positive plate here to the negative plate. Force here is again Q0 E. Now the work done is the difference between these two points, and the difference like we calculated for the gravitational potential energy. So here we'll define EPE, which is electrical potential energy for A, electrical potential energy for B. That is the difference, which is going to give you the work done between A and B. So work done is the difference between the potential, electrical potential rather, energy at A and electrical potential energy at B. To define again, look at the distance the plate is. Let's say at some point it is A, or a point A is here, which is closer to plate positively charged. B is closer to the plate which is negatively charged. So this is the distance they travel, the test charge I mean. That's how you calculate the difference in the energy, which is work done. Okay. Now the next topic is electrical potential difference. The work done depends on the charge Q0. If Q is more, or the test charge value is more in coulomb, the work done will be more. If his Q is less, let's say 3 coulomb compared to 5 coulomb, the work done will be more for 5 coulomb rather than 3 coulomb. So now we have to write in this pattern where work done divided by the total charge equals electrical potential energy divided by the charge, electrical potential energy divided by the charge. So potential energy will count first one for point A, second one for the point B, and see the difference, which will be defined to be work done over the charge. So now we can see here the electrical potential energy per unit charge. This is electrical potential energy per unit charge. If it is 10 coulombs, then potential energy total is 20. So 20 divided by 10 will be 2. Same thing here, if it is 15 and test charge is the same, it's 2. So we have 15 divided by 2, which will be 7.5. I'm sorry. This is called as the first factor, as you see in the circle, is called as the electrical potential, or the potential with the symbol V, and V is defined to be electrical potential energy divided by the total charge. The potential energy unit is coulombs. Coulombs divided by, joules divided by coulombs will give you volts. That's the unit for the electric potential. Now, let's look at the potential difference between 2 points, A and B, which we can write down as B for electrical potential at the point B, take away electrical potential at A, so we can write down EB divided by Q0, EP A divided by Q0, that equals again work done from A to B. See the difference I'm taking between B and A, okay? Potential energy for B, take a potential energy for A, both divided by the charge Q0. So that's why we have a negative sign here. So negative W AB, A to B, divided by Q0. Now as you see on your left side, we have VB take away VA, a change in voltage, so that is delta V. So same way we can on the right side we can write delta EPE divided by Q0 will be equal to negative WAB over Q0. So all you have to do now after understanding this equation here, go to example 1 on page 516, also example 2 on 517. In example 517, we have one point which is A is at a higher potential, C as a lower potential. In between we have B, which is the potential wise in between A and C. Let's say the potential for A is 10, potential for C is 4, then let's say it will be somewhere in between, like 6 maybe, or I'm just guessing a number, any number it could be. But that number has to be in between A and C value wise. So this is an important example, which is 2. So go over this, which will clarify the difference between potential at B, potential at A, or rather we have VB, VA, or VA, VB, which will be delta V. Okay, the next topic we are talking about now is the electrical potential difference created by a point charges. By point charges mean the charge could be a single point, or single charge could be at 2 different points, 3 different points. Let's see a curve as you see here on the figure 19.5. Point A is higher potential, point B is lower potential, and there are 2 charges. One charge is positive Q here, other charge is positive Q, which is the test charge. Now Q, which is the charge, is away from point A, which is distance wise RA, and charge Q here, Q0, which is test charge, is let's say the point we are considering as point B. So that difference between RA and RB will take into account 2 different distances, okay? This Q and Q0 at 2 different points. So we're taking A, which is RA here, and B is RB. The force is acting towards B, or rather from positive charge to the positive test charge. So work done, again, we'll calculate from the Coulomb's law. Coulomb's law says that F equals K times Q1 Q2 over R square. So this is your force, remind you. So force times R will give you the work done. So when you multiply K Q1 Q2 divided by R square times R, it becomes K Q1 Q2 over R. That's what I wrote here. Q times Q0 over RA, because we have Q and Q0 here, okay? For RB we have Q, Q0 and RB, the distance is different. Now we can consider this as an equation where the work done is difference between these 2 potential differences. So you have VB, take away VA is negative work A to B over Q0, which is similar to the previous one. Now look at the figure we had, 19.5. Let's say the point B is moving further away from point A, slowly becomes the distance wise become larger. Let's say it was at 10 meters, now move to 15, 20, 50 and 100 meters, sort of that. In that case, this becomes, this factor we have, which is kq over rb, will be 0 compared to kqra. So the VA, which is the potential difference or the voltage wise, kq over RA, they will be equal. So K times Q, whatever the value of Q is, divided by R, A will give you the voltage at A. So we can divide kq by R and we define the potential of a point charge. So when we divide again kq over R, or the distance, then we will define this to be the potential at a point charge, which is V equals kq over R. This is a very important equation to be used in solving problems. Refer to figure 19.8, page 522. Go over example 5 on page 522. Now the next topic, we're talking about defining the equipotential surface. Now to define equipotential surface, that will be a surface on which the electrical potential is same everywhere. You can very well see in this figure you have 19.11, page 525, and figure 19.12 is 525. Please note here that the capacitor topic will be covered after we finish chapter 20.